All right, this example is quite important. Let us use this quadratic function to develop some very important observation. So for this function, we can start with taking derivative. So derivative of this guy is x cubed minus 3x. So you have nice factoring. X times x squared minus 3. If this becomes 0, we have x equals 0 and plus minus square root 3. So we see this function has horizontal tangent line at x equals 0 and plus minus square root 3. And actually, this is negative square root 3 and square root 3 and then 0. Okay. We take derivative further to get second derivative. So derivative of this guy is 3x squared minus 3. So if we factor, we have x plus 1, x minus 1. If this becomes 0, we have x equals plus minus 1. So actually, this is a graph of f prime. We have plus minus 1. So this is negative 1 and 1. Our second derivative has zeros at negative 1 and 1. Okay, so comparing three graphs, we will examine how derivative of this function affects the graph of this function. So first, our function increases from negative square root 3 to 0. So let me write this down. Our function, this arrow means f is increasing on interval from negative square root 3 to 0. And then from square root 3 to infinity. So we have two intervals where our function increases. By the way, those two intervals are not random intervals. Actually, those two intervals are exactly the intervals where f prime is positive. Sorry, f prime is, so this interval from negative square root 3 to 0 is exactly where f prime is positive. And square root 3, from this to infinity, our function f prime is positive. So f prime is positive on exactly on the same intervals. So we can say whenever your function is increasing on some interval, f prime is positive. That's not surprising. Whenever your function is increasing, the tangent line must be increasing like this. So the f prime must have some positive value. Conversely, if your f prime is positive, then derivative have positive slope. That tells you your function is increasing. Similarly, your function is decreasing from negative infinity to negative square root 3, and then from 0 to square root 3. On those intervals, f prime has negative value from negative infinity to this, and then from 0 to square root 3. So exactly the same intervals. Again, whenever your function f prime has negative value, tangent line has negative slope. That forces your function to be decreasing. Conversely, if your function is decreasing, tangent line is decreasing, so it has negative slope or negative f prime. So two conditions are equivalent. Again, so f is increasing if and only if f prime is positive, f is decreasing if and only if f prime is negative. Okay, local maximum and minimum. Your function has local maximum at 0. So at x equals 0. And local minimum at those points at x equals negative square root 3 and square root 3. So those points are exactly where f prime changes sign. So f prime changes sign from positive to negative at 0. And f prime changes sign from negative to positive at those points. That change gives you local maximum. So f changes sign at x equals 0, and then negative square root 3 and square root 3. On the first point, it changes from positive to negative, and then for those two, it changes from negative to positive. So this change gives you local maximum, and this change gave us local minimum. So we can use the previous observation to see the relationship between f prime and f double prime as well. So our function is concave upward from negative infinity to up to this point, but this point is nothing but negative 1. So our function concave upward on the interval, and then concave upward from 1 to infinity. On those intervals, our f double prime is positive from negative infinity to negative 1, and then 1 to infinity. So concavity of f is exactly determined by sign of f double prime. So f double prime is positive on the same interval. Well, the reason is whenever it's positive, our f prime has positive slope for the tangent line. That means f prime is increasing. F prime increasing means that tangent lines have increasing slope. That's why we have concave upward. So similarly, and then f is concave downward from negative 1 to 1. And on this interval, our f double prime has negative value exactly. So f double prime is negative on the same interval. Well, again, if f double prime has a negative sign, then f prime has tangent lines with negative slope. That means f prime is decreasing. That means f has tangent lines with decreasing slopes. That's why we have concave downward. So two conditions are equivalent again. Concavity is completely determined by the sign of f double prime. And inflection points occur at those 2 points. Inflection points are at x equals negative 1 and 1. Those 2 points are exactly where f double prime changes sign from positive to negative, from negative to positive. So f double prime changes sign at x equals negative 1 to 1. That's where we have inflection points. So in the next slide, let us formulate our observation carefully. So as we observed in the previous slides, f is increasing on some interval if and only if f prime is positive on the same interval from A to B. So sign of f prime determines where f is increasing. Similarly, f is decreasing only when, if and only if f prime is negative. So two-sided arrow stand for two statements are mathematically equivalent. So we apply this observation to f prime. F prime is increasing if and only if its derivative is positive. So in other words, f double prime is positive. Similarly, f is decreasing if and only if its derivative is negative. So its derivative, f double prime, is negative on the interval. Concavity is determined by the sign of f double prime. So f is concave upward if and only if f double prime is positive on the same interval. And then f is concave downward if and only if f double prime is negative. On the same interval. And inflection points occur when f double prime changes its sign. So whenever f prime changes the sign, original function f has inflection points. So let us use this observation and theorem throughout the section. And we will use this observation to sketch the graph and describe behavior of the function.